And C++ is also hard to write, so it's more difficult to find good examples for this, but I think this one illustrates the point well. So if you look at cin, which is like it's a part of standard C++, it's the standard input stream, it has a type conversion to void pointer. And that looks kind of strange, because why would you need a void pointer? And it turns out that what they really wanted was this. So it looks like they really want a bool, right? But because C++ inherited from C, if it was a bool, then you could write this expression, which is wrong because it's trying to write, right? This is not cout, but cin. So this would still compile, because the bool would be converted to an int implicitly, and the shift would be done on the int, and the result would be discarded. So they said, okay, to make this right, we need to make it a void pointer. And this small, I mean, who of you, if you write a piece of code and it returns a bool, would think of this, right? So this is the kind of words that I think that you need to know if you want to write a good library. And that's why writing good libraries is really hard in C++. So there's some other stuff that's partially known, hopefully, in C++ programmers. So I have extra pages for all of these. There's just the list. So you can throw exceptions in destructors, and you shouldn't throw exceptions in constructors. And there's all of these things have good reasoning behind them. So none of these is like, oh, I'm going to piss on the developers. But they have good reasons for all of these. But still, in the end, you have to know all of them. And this looks really stupid. Why would you have exceptions if you can throw them in a destructor, right? So the initializer is done. This is a little esoteric. I have a good example on that. Auto-PTR is the standard C++ idea of how to do garbage collection with a poor man's garbage collection. And it's completely broken, really, so you shouldn't use it for anything. I have an example on that, too. So another design decision with C++ was that iterators shouldn't know anything about the container. And this leads to all kind of interesting breakage if you misuse iterators. I have examples for that, too. And for vector, and this really bugs me, because why would you have a special vector class and say people don't use the arrays anymore because there's no range checks in the arrays? And then they have this vector class, and they don't do bounds checking in the operator. It just doesn't make sense. And it's historical, so in the early C++ compilers, this there was a high abstraction penalty. We call it abstraction penalty these days. There was a high penalty for the compiler was unable to inline it, really. And so the code was not guaranteed to be like fast enough, so they said, okay, so we leave the option open. And GCC still doesn't do this. So another thing that's really unclear how this can happen, but if you think about it, it becomes clear. So you can't call virtual member functions from the constructor and the destructor, which is less evil, but the constructor is bitten a lot of people. So let's say you want to throw an exception from a constructor or a destructor. So the destructor is the easier one to understand why you can't do it. So let's say you have this delete operation on an array with 10 members, and the second one throws an exception. Then what do? The other ones are still not destructed. So if you say, okay, I'm ignoring the exception and I'm still destructing the other ones too, and another one throws an exception, then you would have two outstanding exceptions, and C++ can't have that. So that's why you can throw exceptions in destructors. So as I said, there's a good reason for everything in this. So, but still, in the end, it's like, what the hell? So in constructors, it's different. And one of the problems with constructors is that they don't return an int or something. So you can't use the error value to say that you failed. So you have to use an exception if you fail for some reason. So one of the problems is that if you throw an exception in the constructor, the object isn't set up properly. So the destructor isn't called on the constructed object itself. So if you initialize anything in the object and then fail halfway, then it's never freed. You have to do that yourself. So you have to catch your own exception, really, or do before throwing, just uninitialize the stuff you already did. And this wouldn't be so bad if C++ wouldn't have the major selling point of the stack being unwound for you. And not even the local stack is cleared up. And I couldn't believe this myself, but you're welcome to try this. Don't believe anything I tell you. This is all, you should test it yourself. Not even if you have a local variable on the stack. I think I have a test. Okay, so this is still... I think I have one for those too. Yeah, okay, so... So this is just a small test program. You probably won't be able to read it. Just all the constructors and destructors just say they're being called. And I have this test class that includes this verbose class on the stack locally and then throws an exception. And you can see that the constructor is called twice, but it's never destructed. So neither the object that I'm trying to construct is destructed, but also the stack isn't cleared up properly. So that's really horrible, right? And so you have to use your own cleanup. And this is stuff that usually isn't tested for, right? You test the cases that look like they might happen, and most people don't think that stuff could fail in the constructor and throw an exception. But it happens all the time. For example, if you allocate some memory and there is no memory left, then you get an exception. So the initialization order, it looks like it shouldn't be an issue. I have this contrived example here. So I have this class that has a pointer, and it's my own array, right? It's like a vector. So what I'm doing here is that I have n, and that the constructor gets the desired size of the vector. And at first, it puts the n in allocated, which is a member, right? Then it says used is 0, and then it allocates this amount of members. And in C++, it's not this order that matters, but it's this order. So what happens here is that the thing being done first is the data initialization, and at this point, allocated wasn't written to. And this is the kind of stuff you wouldn't expect if you write code, right? Because usually in C and C++, the comma operator says the left side is done first, and then this is done, and then this is done. And this is the kind of stuff that you can shoot yourself in the foot and not even notice, right? So this actually happens from time to time. There's web pages about this, and people filing bugs against GCC, and the GCC people saying, but this is the standard says it should be like this. So about auto PTR. So it's supposed to be the garbage collection wrapper around a pointer. So the idea is that if you have a constructor or some function that can throw an exception in the middle, then you use auto PTR. And once it goes out of scope, for example, because an exception was thrown, then it frees the memory. The problem is they don't have any reference counts or something. So if you have two auto PTRs and you do an assignment between those, then the first one, the original one, doesn't own the object anymore. And this in C++ can happen implicitly. You can write a statement that looks nothing like an assignment, but GCC or the compiler has to create a temp object, and at that point you lose the contents of the auto PTR. So this means no explicit assignments. Okay, you can live with that probably. You can't pass it by value into functions. And it breaks when you put it in STL containers, because those reserve the right to copy the members all the time. So you have this pointer that you really can't do anything with. And this is like typical for parts of the C++ standard. The first iteration usually sucks. And the people understood this, and there are better alternatives in the next version of C++ that's being debated now. But they ship this, and there are books out there telling you to use it and how not to shoot yourself in the foot while doing it. But, I mean, ignoring it is easier than just not shooting yourself in the foot and using it. I said that iterators just don't know anything about the container. So if you do something like this, you have container A and call remove with an iterator that points to another container, you get silent breakage. So if it's a list, then what this does is remove the object from B, but decrease the size of A, which is, it's wrong, obviously, right? So you get very weird effects suddenly. And this could be checked, but it isn't. And they're not even debating if it should be checked because it's a performance issue, right? So other problems could be that if you have an iterator to an object that was removed, like in a different thread maybe, or you just removed it yourself. So for example, you have this list and you want to remove all the members where the first character is an S, right? So what would you do? You just use an iterator, walk through the list, and if it starts with S, you say delete, right? Or remove, it's called remove. But that invalidates all the iterators. So the way you would have to do it safely would be to restart from the beginning and again look for the first one with an S. So the STL does some wrapper that does this for you, but I mean it still stinks, right? So there's cases where this is not so obvious. For example, if you have a balanced tree, which is used for the map, for example, in C++, and then you delete some other object in this collection, then the tree might rebalance. And the iterator is just a pointer, really, so it doesn't know that the tree was reshuffled. So it points somewhere, and if you use it, then it might work most of the time, but sometimes it stops working, and then it's a pain in the ass to debug this. Or even worse, if someone destructed the container, then the iterator doesn't know anything about it, and you have memory corruption. So all this abstraction, usually you do this kind of abstraction so you don't have to do the checks yourself. But in C++, you get the abstraction and you have to do the checks. So this bounce checking thing is another pet peeve of mine. I have another talk on the third day about what optimizations in code you shouldn't do because the compiler already does them for you and you only make the source code worse. And this is one of them. So if you're interested in this, then come back on day 3. But in C++, I find there's really no excuse why they wouldn't say that this operator also does bounce checking. It just doesn't make any sense. So calling virtual function in the con and destructor is really horrible because the C++ standard says after the destructor, after the constructor is done, only after all the code in the body is executed, only then is the vtable updated so the object is officially of the class that's being constructed. And the rationale for this is that until you have initialized everything, it isn't really the new class. So if you call some virtual member function in the constructor, then the vtable still points to the vtable of the class that you inherited from. Right? So if you have a virtual function, for example, if it's an abstract base class, which is a well-known concept in object-oriented programming, and you call the function that you in the class that inherits and provides a real implementation for it, then the program terminates because you called in a pure virtual function. And that's kind of surprising if the first time it happens to you. So all this stuff. I have this list of statements, and so the basic idea for the talk was to have this really small statement and then find ways how it could behave unexpectedly. And so this one didn't really fit in the others, so I have a special slide for it. But it illustrates the kind of problem you have as a code auditor. So I have this type. I have some type A equals B, and then I change some member in A. So if you come from C, then you would say, okay, so B isn't modified here, but that's not true. It's not clear. So you could define the type, so that's a reference to other type. And then this doesn't actually create a copy, but both point to the same memory. And if you audit code, you have to check if this is true. Even if the guy who wrote it would never do that, but you still have to check it because that's the job of the auditor, right? So all this crap you have to look at in C++ really makes auditing hard. So this is the statement in the end that I came up with to see how not easy it could be. So it looks easy. You have this basic idea. So for example, Baz could be an int, and this could be some kind of struct with a pointer to something, function pointer, and you pass an int. But it could also be a reference. Baz could be a reference. And then we override something else. It could even be a reference to foo. And someone could have provided this operator for it. And then suddenly in the next line, foo is changed. Or it could be a class with its own operator. It could be a smart pointer. And then I would have to look at the code that implements it to see maybe every statement in there could look this easy but have the same trail of crap you have to check. And bar could be a member function, obviously, but it could be a reference, and it could be alias something else. So, and if you the next question is which buzz is it? So there could be like in the root scope, or there could be namespaces, and you can't tell from this line. So usually what you do in C++ is you're using namespace, whatever, but there can be more than one of these statements. And they can be anywhere. They can be like 1,000 lines before. They can be in a different file that's included somewhere. So you have to chase all the way for this. And what if it's using more than one namespace? Then you have to look at those namespaces too to see if it has those. And so you end up chasing all the way in the whole project. So then there could be templates. You've probably been waiting for this. Could be templates. Maybe it's more than one template. And maybe there's an